The bowling scores of a college team member over the 26 games played for a year are shown in the scatter plot. Separate the data into appropriate intervals and choose the function types that would reasonably model the intervals. Generate a function model for each interval of the dataset using finite differences, successive ratios, average rates of change, or regression models. Okay, so let's first look at our graph and see where the natural intervals would occur. So we see at first it comes down and curves a little bit. That looks like it could be a parabola there. And then it comes up and goes fairly straight for a while. And so, maybe we could do a parabola and then a line or a quadratic and linear there. And so it looks like from about 0 until 5 is when that looks like it could be part of a parabola, and then that turns into a fairly straight line of dots until about week 15 there. And then again, it comes up and curves a little bit, which could be another quadratic. That one would be upside down, so it's curving the other way. And that goes till about week 21, where then it just takes off in a that could be even linear or maybe even exponential, that very steep line there. And so let's go ahead and divide that up in the table. So now we have our intervals. We have many ways that we could find models for each of these intervals, but let's go ahead and just start by finding finite differences. So the first one we expect to be quadratic. Let's go ahead and find the first set of differences. So 56 minus 53 is 3, 53 minus 52 is 1, and so on. And those are not very similar, so let's go ahead and find the second set of differences. So 3 minus 1 is 2, and so on. And so we see that the second differences are much more similar. Almost all are 2, and then there's 1, 3. So if we add those up and divide by 4 to get the average, then we get 2 and 25 hundredths. And so using our rules about quadratic functions, since those are the second differences that were similar, then 2a equals the second difference, which we averaged to 2 and 25 hundredths, and then dividing by 2 on each side, then we get a equals 1 and 125 thousandths. And then we know that a plus b equals the first difference between x equals 0 and x equals 1. So in this case, that'll be negative 6. So then plugging in 1 and 125 thousandths for a, we would subtract that to get b alone. And so we get b equals negative 7 and 125 thousandths. And c is just the y-intercept there. So when x is 0, then the y value is 64. So if we call this equation f of x, then subbing in a, b, and c into a quadratic function, then we get f of x equals 1 and 125 thousandths x squared minus 7 and 125 thousandths x plus 64. So let's go ahead and go on to week 6 through 15. This is the one that looks pretty linear there. Let's go ahead and find the first differences for this interval. So 99 minus 97 is 2, 97 minus 93 is 4, and so on. So our first differences are not incredibly similar. As we can see in the dots, it's not a perfect straight line, but we'll go ahead, since that looks fairly linear, we'll go ahead and average these to find our first difference. And so adding those all together and dividing by 9, then we get 4.1 repeating, or just 4 1/10 if we round it. And so here, if we call this function g of x, then we'd have g of x equals 4 1/10 x, and then plus the y-intercept. And we don't have an x equals 0 in this interval, and so we need to use point slope form here. So let's use our first point, 662, and we'll plug that into our point slope form to find what b in our y equals mx plus b equation would be. And so we would have g of x minus our y value, 62, equals 4 1/10 times x minus 6, the x value. So then distributing, we get 4 1/10 x minus 24 and 6/10, and then adding 62 on each side to get g of x alone. Then we get 4 1/10 x plus 37 and 4/10. So for our next interval, since we've done a lot of finite differences, let's find this one by using a regression model. And so if you go to Stat and then Edit, and then in List 1, we'll go ahead and put in the numbers 16 through 21, and List 2, we'll put in 105 through 115. And so now we can press Stat, and then Calc, and then go down to Quadratic Regression, since this interval looks like it could be a parabola that's facing downward, and then press Enter. And we see here we have our a, b, and c value. Let's go ahead and round our a value to the nearest hundredth, and then the b and c value will just round to the nearest tenth. And so calling this h of x, then we get negative 82 hundredths x squared plus 32 and 4/10 x minus 203 and 1/10. Let's go ahead and find for our last interval. And so our last interval, let's try finite differences again. And so here we have, a really wide difference from 18 to 40. That maybe could be linear, but these first differences are really different. So let's actually try a different method and try successive ratios. And so taking 221 and dividing it by 197, then we get 1 and 122 thousandths if we round to the nearest thousandth. Let's divide the next pair. 197 divided by 157 is 1 and 255 thousandths, rounding to the nearest thousandth. And we'll go ahead and do the next two. And so these are all pretty similar, so I think an exponential equation would be smart here, would be a more reasonable model. So adding those all up and then dividing by 4, then we get 1 and 275 thousandths, rounding out to the nearest thousandth. And so calling this j of x, then we have j of x equals, and then we don't know the value when x is 0, so we're going to have to solve for that. We'll just call it a, and then we have our ratio raised to the x, since our delta x here is 1. And now to solve for a, then we just need to pick a j of x and x value, so let's pick 22 and 116. And so then j of x would be 116, and then equals a times 1 and 176 thousandths raised to the 22nd. So simplifying 1 and 176 thousandths to the 22nd and rounding that to the nearest thousandth, then we get 35 and 397 thousandths. And so then to solve for a, then we just need to divide by that number on both sides. And so doing that and rounding to the nearest hundredth, then we get 3 and 28 hundredths. And so now substituting that into a, then we get j of x equals 3 and 28 hundredths times 1 and 176 thousandths raised to the x. And so now let's go ahead and graph these various models and put them on top of our scatter plot and see how well they actually fit our points. So here you see we have our scatter plot and the different intervals, and then we have the function that goes with each one. And we see that f of x, most of them actually are really quite good in that most of the dots go through the line, and g of x is probably our weakest since many of those dots are right above the line, but still fairly close, and so these are fairly reasonable. And I have included in the answer the equations found using the finite differences as well as the regression models if you chose to do those for other equations. Let's go ahead and summarize. The functions written from the data values are a reasonable fit as the functions are fairly close or intersect with most of the data points. See scatter plot and graph to the right. Function types for intervals: week 0 to 5, quadratic; week 6 to 15, linear; week 16 to 21, quadratic; week 22 to 26, exponential. Equations found using finite differences: week 0 to 5, f of x equals 1 and 125 thousandths x squared minus 7 and 125 thousandths x plus 64. Week 6 to 15, g of x equals 4 and 1/10 x plus 37 and 4/10. Week 22 to 26, j of x equals 3 and 28 hundredths times 1 and 176 thousandths to the x. Using regression, week 0 to 5, f of x equals 1 and 16 hundredths x squared minus 7 and 4/10 x plus 64 and 1/10. Week 6 to 15, g of x equals 4 and 8 hundredths x plus 39 and 67 hundredths. Week 16 to 21, h of x equals negative 82 hundredths x squared plus 32 and 4/10 x minus 203 and 1/10. Week 22 to 26, j of x equals 2 and 88 hundredths times 1 and 182 thousandths to the x.